Let's now look at some examples where we are given an iterated integral in x and y, and we think it will be advantageous to switch to an iterated integral in r and theta. So in order to make the substitution, of course I know I'm going to let x equals r cosine theta and y equals r sine theta, but I also need to know the bounds I'm going to be integrating inside of. So it's probably going to be helpful if we have some idea what the region of integration looks like. So let's draw an xy plane. And I can see that all of my bounds are positive in x and y, so I'm going to be in the first quadrant, it looks like, because I'm 0 to something positive and 0 to 2. So my y is running between 0 and square root of 4 minus x squared. 4 minus x squared is the semicircle of radius 2. And that, of course, just comes from, we know the equation for a circle, x squared plus y squared equals the radius. So if I solved that equation for y, I'd get square root of 4 minus x squared, the semicircle. But I'm in the first quadrant, and my x is going to run from 0 to 2. So my y is running from 0 to the semicircle, and my x is running from 0 to 2. So this is the region over which I want to integrate. Now I want to describe that region in polar coordinates. Well, it seems pretty clear to me that the theta is moving between the angle 0 and the angle pi over 2. So theta equals 0 and theta equals pi over 2. And my radius is between 0 and 2. So if I want to write that in polar coordinates, my theta bounds are going to be 0 to pi over 2, and my r bounds are going to be from 0 to 2. But I also have the function of xy, x squared plus y squared to the 3 over 2. So I want to switch that in terms of my substitution. So that's going to be r squared cosine squared theta plus r squared sine squared theta to the 3 over 2. R dr d theta. Again, this r is coming from my Jacobian. So that's 0 to pi over 2, integration 0 to 2, r squared to the power 3 over 2 is to the power 1/2 cubed. And I know that r squared to the power 1/2 should give me absolute value of r. But I also know that my r is positive. It's between 0 and 2. So I'm going to write r cubed times r dr d theta, because I got r squared, I got absolute value of r cubed, but then I determined that I don't need absolute value because I know my r is positive. All right, so that's clearly integration 0 to pi over 2, integration 0 to 2, r to the power 4, dr d theta. So the antiderivative of r to the power 4 is r to the power 5 over 5, evaluated between the limits 0 and 2. Then I'll integrate with respect to theta. 2 to the 5th power is 32. So this is integration 0 to pi over 2. 32 over 5 minus 0 d theta, and the antiderivative of the constant is the constant times theta between 0 and pi over 2. So I have 32 over 5 times pi over 2, which is 16 pi over 5. So I transformed the given integral in terms of the polar coordinates, and that made it super simple to integrate. I get 16 pi over 5 as my result. There's one more example here where we're given the sum of two iterated integrals, and the question tells us that we can write that sum as a single integral if we change it to polar coordinates. So let's think about what this region might look like. I see that in the first integral, I'm between 0 and 5 square root of 2 all over 2 in terms of y, and then in terms of x, and then y is between 0 and x. And in the next one, my x is between 5 square root of 2 over 2 and 5, and my y is between 0 and square root of 25 minus x squared. So again, I conclude I must be in the first quadrant because everything is positive. So let's look at y is between 0 and x. We know that the line y equals x is just the diagonal line. So I know that in this first integral, y is between 0 and x is between 0 and 5 square root of 2 over 2. So let's just say here's x equals 5 square root of 2 over 2. All right. Now, in the second integration, I have y between 0 and square root of 25 minus x squared. I know that square root of 25 minus x squared is again a semicircle, and it's going to be a semicircle of radius 5, just like in the previous problem we had the semicircle of radius 2. Semicircle of radius 5. And if I want to know where the line y equals x and the semicircle cross, I can solve 25 minus x squared is equal to x. So 25 minus x squared is equal to x squared. So 25 is equal to 2x squared. So 25 over 2 is x squared. So that's 5 over square root of 2 equals x, which is 5 square root of 2 over 2. And that, of course, is why I drew it this way. This point of intersection of these lines is going to be 5 square root of 2 over 2, comma, 5 square root of 2 over 2, of course, because it lies on the line y equals x. So the region of integration that these two integrals are describing, first I have y going from 0 to the line, x going from 0 to 5 square root of 2 over 2. Next I have y going from 0 to the semicircle, and x going from 5 square root of 2 over 2 to 5. And clearly, if I change this into polar coordinates, I can do it in one simple integration. So let's do that. So in terms of polar coordinates, I need to know bounds for the radius and the angle theta. So I'm going to note here that the line y equals x is exactly halfway between the angles 0 and pi over 2. So here, theta is equal to pi over 4, and r is between 0 and 5. And we are integrating a function of x and y, which is x times y. So the integration will become my bounds for theta, 0 to pi over 4. My bounds for r, 0 to 5. X times y is r cosine theta times r sine theta times r dr d theta. This r coming from my Jacobian. So that's 0 to pi over 4, integration 0 to 5, r cubed sine theta cosine theta dr d theta. My first integration is with respect to r, so I'm going to consider theta as a constant. So this is 0 to pi over 4, r to the power 4 over 4 sine theta cosine theta, evaluated between 0 and 5, and then I'll integrate with respect to theta. So that's integration 0 to pi over 4, 5 to the power 4, 625, and of course 0 to the power 4 is 0. So I'll pull my constant out. We had a similar integration in a previous video where we discovered we could do a u substitution. I can let u be sine theta, then my du is cosine theta d theta. That's nice and easy. But we can also do this using the double angle half angle formula. So sine of theta cosine of theta is 1/2 sine 2 theta. Antiderivative of sine of 2 theta is minus cosine of 2 theta over 2. Evaluated between 0 and pi over 4. I have 625 over 16. Cosine of 2 times pi over 4, cosine of pi over 2 is 0. Whereas cosine of 0 is 1. So that doesn't seem quite right. Let's see. Right, so sorry about that. So cosine of 2 theta, when I plug in pi over 4, I get 0. And then I get minus, when I plug in 0, I get 1. So that's minus 1. So that's 625 over 16 times 1. And that is the value of this iterated integral. So as you can see, quite simple once we changed it into polar coordinates, whereas it might have been quite a bit more difficult if we left it in rectangular coordinates.